Hi, I'm Ms. Hearn. Let's get started. In this video, we're going to fill in a hole in a rational function by defining it appropriately. The key is to find the y value of the hole and define the function to have that value. So in the graph that we're looking at right here, you can see there's a hole at the x value 1. We want to fill that by saying, okay, let's let that y value be blank. Problem is that we don't know what that y value actually is here. So the challenge is to figure that out. But there's a very easy way to do it. So let's get started. The exercise we're going to work says define f of 4 in a way that extends f of s equals s cubed minus 64 over s squared minus 16 to be continuous at s equals 4. Here are some facts that we will need to remember. First of all, what does continuous mean? Continuous means that there's no holes, gaps, or jumps in the graph. Now we know that rational functions, like this one, that are fractions made of polynomials, are undefined and either have holes or asymptotes wherever the denominator is equal to 0. We also know that if you reduce that rational function to lowest terms, the new reduced version of the function has the same graph as the original, except any holes have been filled in. This doesn't mean that asymptotes have disappeared, just the little tiny holes in the graph, the open dots on the graph. In this particular problem, we're going to also need to remember our factoring rules for binomials, for two-term polynomials. Remember, a binomial can only factor if it fits one of these three patterns: a difference of squares, a difference of cubes, or a sum of cubes. So to work our exercise, the procedure that we're going to need to do is to find the reduced form of the rational function and then evaluate it at the point where the original function had a hole. So I'm going to start by writing down my original function, f of s. I'm going to factor it. I know that I need to use the difference of cubes formula for the numerator because s cubed minus 64 is the same as s cubed minus 4 cubed. And I'm going to use a difference of squares factoring formula for the denominator because it's the same as s squared minus 4 squared. In this case, a is s and b is 4. So we're going to have a minus b, so s minus 4, times a squared, so s squared, plus s times 4, so 4s, plus 4 squared, which is 16. And in the denominator, we use the difference of squares factoring formula. That's going to be s minus 4 times s plus 4. Now notice that this is equal to s squared plus 4s plus 16 over s plus 4 if we cancel. Well, almost equal. It's equal everywhere except at 4. Can you think of why these two expressions would not be equal at 4? Because if you plugged 4 in for s over here, you would get undefined. But if you plug 4 in for s over here, you're going to get another value. So really, I can't really say these two are equal unless I specify they're equal everywhere except at 4. Now remember, 4 was the value that we were asked to investigate. And it's important to understand why we were asked to investigate that particular value. Not only is the function f undefined at 4 because s minus 4 equals 0 when s is 4, it's also undefined at negative 4 because the denominator would also be 0 at negative 4. But there's a difference between the way the function behaves at these two undefined values. At s equals 4, there's a hole in the graph, and the reason I know that is because it cancels. At s equals negative 4, however, that factor of s plus 4 doesn't cancel, telling me that the function actually has a vertical asymptote at this value. We were asked about s equals 4 because this is what's called a removable discontinuity. We can define the function at 4 so that we have a nice smooth curve with no holes in it. And the way that you do that is you compare the function to what I'm going to call the reduced version of f, r sub f, which is just the s squared plus 4s plus 16 over s plus 4 4, and I'm not going to say s can't equal 4. So this is a different function, but it's only different at one value, s equals 4. So to figure out how we want our function to be defined so that it doesn't have a hole, we evaluate this reduced version at 4. So the reduced version of f at 4 would be equal to 48 divided by 8, which is equal to 6. This tells us that the only difference between our original function f and our reduced version of the function is that f had a hole at 4 and this new function has the value 6 at 4. So if we want to fill the hole in for f, we could say define f of 4 to be equal to 6. And we know that that will fill in the hole. I hope you found this video helpful. If you did, please give it a thumbs up. That will help other students to find the video. And for more math videos, subscribe to my channel, Miss Hearn Mathematics.